Our goal for this lesson is to understand and solve problems that involve independent events. Independent events. If the probability of event B does not depend on the probability of event A occurring, then these events are called independent events. For example, tossing tails with a coin and drawing the ace of spades from a standard deck of 52 playing cards are independent events. They don't depend upon each other. They're two totally different ideas. The probability that two independent events, A and B, will both occur is the product of their individual probabilities. So the probability of event A occurring times the probability of B occurring. So let's think about this. Anne and Abby each have 19 marbles, 11 red and 8 blue. So they each have 19. Anne places 7 red marbles and 3 blue marbles in bag 1. She places the rest of her marbles in bag 2. Abby places all of her marbles in bag 3. Anne then draws 1 marble from bag 1 and 1 marble from bag 2. Abby draws 2 marbles from bag 3 without replacement. Are both girls equally likely to draw 2 red marbles? Maybe if you would like, pause this for a minute and try it. See if you can come up with an answer. What we have, let's have a look at Anne. Now Anne has 2 separate bags. In the first bag, she's going to draw 1 marble, and in the first bag, she has 7 red and 3 blue. We want to know she's going to draw 2 red marbles. So first of all, in that first bag, she has 7 red marbles, and there are 10 marbles in the bag. In her second bag, there are 4 red marbles, and there are only 9 marbles in the bag. So when we calculate this probability, we get 28 out of 90, or we can write it as 0.3111, or 31%. So she has about a 31% chance of drawing 2 red marbles. Let's have a look at Abby's situation. Abby placed all of her marbles in the same bag. She's going to draw 2 marbles without replacement. Remember from the previous lesson, without replacement is dependent, so we have to consider how many are left after making the first draw. So she has 11 red marbles out of 19. Once she chooses a red marble, there are only 10 red marbles left in the bag out of 18 marbles. So that when we multiply those together, we get 110 out of 342, or 0.3216, or a 32% chance. So they are fairly close, but not exact. It does make a difference. In Anne's situation, we had 2 independent events. They were coming from 2 separate bags. So what happened in the first one didn't affect what was going to happen in the second one. But in Abby's situation, all of her marbles were within 1 bag. So what you picked for the first time makes a difference as to what we can pick for the second one. Those are dependent upon each other. A euchre deck consists of the 9, 10, Jack, Queen, King, and Ace of all 4 suits. This results in a euchre deck of 24 cards. Audrey draws 2 cards from a well-shuffled euchre deck. Determine the probability that both cards are queens if the first card is replaced. So she's going to draw a card, she's going to look at it, she's going to place it back into the deck, shuffle it up, and she's going to draw a second card. So let's consider what would happen here. How many queens are there? There's 4 queens in a euchre deck. There are 24 cards in a euchre deck. That's the probability of drawing a queen on the first pick. Now we want a probability of drawing a queen on the second pick. She's put the card back. So there are still 4 queens in the deck. There are still 24 cards in the deck. Multiply those together, we get 16 out of 576, or 0.02777, or approximately 3%. So she has approximately a 3% chance of drawing both queens, putting the first one back in the deck. How about if the first card drawn is not replaced? So we pull it out and we leave it out, and then we draw the second card. Well, first probability is the same. There are 4 queens out of 24 cards. But now we've pulled out a queen. Now there's only 3 queens left in the deck. There's only 23 cards left in the deck. Multiply those together, we get 12 over 552, which can be written as 0.0217, or approximately 2%. So a little bit of a difference. One was closer to 3%, one was just over 2%. Are the above independent or dependent events? Well, if we look at part A. Part A, we replaced the queen. So when we were doing our second draw, nothing had depended upon the first because we put the card back and it was exactly the same as in our first option. So those are called independent. When you have with replacement, you are generally dealing with independent events. But in B, we didn't replace that first card. So the second probability depended upon what happened in the first probability. So these are dependent events. Chase estimates that the probability of passing math is 0.8, and his probability of passing English is 0.7. Determine the probability that Chase will pass both math and English. Now, think about this. Are they dependent or independent? These are independent events. Passing math has no effect on whether or not he's going to pass English. They're at different times, he's doing different courses. They are independent events. So we simply, if he's going to pass both, passing math is 0.8, passing English is 0.7. We can multiply those probabilities together, 0.56, or a 56% chance that he's going to pass both. What about if he's going to pass math but fail English? Well, we know he has a 0.8% chance of passing math. What's the probability that he's going to fail English? Think about this. Remember your complements. He's either going to pass or he's going to fail English. They have to total 1. So if the probability that he's going to pass English is 0.7, the probability that he's going to fail English is 0.3. So we've got 0.24 or a 24% chance of this happening. What's the probability that he's going to fail both math and English? So again, we're looking. What's the probability that he's going to fail math? Well, it was a 0.8 probability that he's going to pass. Passing math and failing math are complements, so they have to add to 1. So it's 0.2 is his chance of failing math. We already determined that 0.3 is his chance of failing English. Multiply these together, we get 0.12 or 12%. In this example, we have 1,000 tickets for a charity raffle have been sold and placed in a drum. There are going to be 2 draws. The first draw is for the grand prize, and the second draw is for the consolation prize. After each draw, the winning ticket will be returned to the drum. So remember I said we need to watch whether it's with or without replacement. The winning ticket will be returned to the drum so that it might be drawn again. Max has bought 5 tickets. Determine the probability to the 10th of a percent that he will win at least 1 prize. Now this question here has a few things to consider. This at least makes it a little bit of a different type of question. Because at least means he could win 1 prize or he could win both prizes. We could consider finding the probability that way. Or we can also do this in one kind of step. The probability that he's going to win at least one prize is the complement of the probability that he wins no prizes. So if we find the probability that he wins no prizes, we can then find the difference when we subtract it from 1. So this is saying the complement of no prizes. So let's find the probability that he doesn't win. He bought 5 tickets. There were 1,000 tickets sold. That means 995 of the tickets are not his. Once one is pulled out, it gets replaced back in. It's going to be returned. So there are still 995 tickets out of 1,000 that are not his. So when we multiply this together, we get 990,025 out of 1,000,000, which is 0.99025. We want to find, however, remember that's the complement. Complements add to 1. So we simply go 1 minus 0.990025. We get 0.009975. And remember, we wanted it to the nearest tenth of a percent. Well, this is going to be 0.99%, which is to the nearest tenth, it's about 1%. So he has a 1% chance of winning at least one of the prizes. So with independent events, that is when we are replacing an item after we've considered it already. That is one example. So they aren't dependent upon each other. You simply find the probability of each event and you multiply them together.